Alrighty, my good people. So now let's put those two ideas together. We know that a function is increasing when the derivative is positive. We know the function is decreasing when the derivative is negative. And we now know that critical points tell us where the derivative is equal to zero or undefined. And those are the places where it could change from increasing, decreasing, and provide us some insight into maximums and minimum points on the graph. So a couple of things to remember. So when we're finding intervals where the function is increasing or decreasing, we can follow this little recipe. Take the derivative. We did. Find where the derivative is equal to zero or when the derivative is undefined. That would be find the critical points. Number three, create a sign chart and test intervals around the values of x from step two. So step two is important because it's going to help us find the critical points. And if those are the only places where the derivative is equal to zero or undefined, then it's going to split up our x-axis into intervals where it might be increasing, decreasing, increasing, whatever it is. And then interpret the sign chart to find the appropriate integrals. If we're given a graph of f prime, then we don't need to create the sign chart because we already have the derivative right in front of us. So we don't need to create a sign chart. I usually do anyway, but you'll get into that idea to see if it's helpful for you. Okay, so let's start it. Let g of x be this quadratic, x squared minus 3x minus 21. Can you find the intervals where the graph of g is increasing and decreasing? Well, if it's a quadratic, that means it's a parabola. If it's a parabola, then it's only increasing and then it's decreasing. Or I'm sorry, decreasing and then it's increasing. So this might be a little bit quick, but let's follow the process to make sure we understand the process. Step one, take the derivative. 2x minus 3. Step two, find the critical points. How do we find the critical points? By setting the derivative equal to zero or undefined. But as I'm looking at this derivative, that's a linear function. Linear functions are not undefined, so I'm going to set it equal to zero and work off of that to find the critical point. Add this over, divide by 2, and so 3 halves or 1.5 is my critical point. Great. Step number 3, and this is something we hadn't thought of doing, and although we did do it when we were doing velocity and acceleration, so maybe that will be a helpful memory. So I'm going to make this sign chart. I'm going to put x values down here. Specifically, I'm going to start by putting the critical point x value. So somewhere here is 3 halves. So think of this as your x-axis. So my x-axis tells me it's 3 halves. However, I know that my derivative, the reason that's special is because my derivative is equal to 0 at 3 halves. But now I'm going to check a point on either side of 3 halves. So I'm going to pick a point bigger than 3 halves, like 2. And but I could have picked any number, right? I could have picked 3, I could have picked 1.9, I could have picked 100. And I'm going to plug any number that's to the right of 3 halves into my derivative equation. I'm not really concerned with what the answer is. I'm concerned whether my answer is positive or negative. Because remember, if the derivative is negative, my function is decreasing. If my derivative is positive, my function is increasing. So when I substitute this in there, and I get 2 times 2 minus 3, that's positive 1. I'm going to put a plus sign here because that tells me that my derivative is positive. But I could have chosen any point to the right of 3 halves. So that means my derivative is positive in all of this section. Now, I'm going to pick a point on the other side of 3 halves. Another point like 0. And I'm going to substitute that point into the derivative. I could have chosen any point to the left of 3 halves. I could have chosen 1. I could have chosen negative 10. But I chose 0. You can pick another number and try it. You're going to get a negative answer. I'm going to put a little negative here. But you could have chosen any number. So anything on this side produces a negative derivative. So what does this tell me? This tells me that the original function, g of x, is decreasing, and then it's increasing around x equals 3 halves. Have I answered the question? No. Let's answer the question. G is increasing on the interval for x values that are bigger than 3 halves. So x's that are bigger than or equal to 3 halves. And I'm even going to say how I know that. Because G prime is positive, but most people will write G prime is greater than or equal to 0. Okay. What about decreasing? G is decreasing, and you're saying, aren't you doing a little overkill? Isn't this a little much? Isn't this a little extra, Mr. Orientes? I need to answer the question, or else I don't get credit. I need to answer what they were asking. Find the intervals where G is increasing, where G is decreasing. G is decreasing on x values that are less than or equal to 3 halves. And I know that because G prime, and I'm just going to do less than or equal to 0. How about that? And we're done. Now, here's a preview of the next section. The next section says, can you find out where the graph has relative minimums, like little valleys, and relative maximums, little hills? Well, just by looking at the sign chart, we can tell there's going to be a relative minimum at x equals 3 halves because the graph is going down and then it's going up. So it must have had a minimum point at x equals 3 halves. Do I know what the y value is? No, although I guess I could substitute 3 halves into the formula to figure it out. But at least we know there's a relative minimum in this graph, which we could have predicted because we knew it was a parabola. Okay, so the idea is, number one, take the derivative. Number two, find the critical points. Number three, set up a little sign chart. Number four, and I'll put the number 4 here, is interpret what the sign chart is telling us. It might seem like it's a lot, but it really is an organized way to accurately find the intervals of increasing and decreasing. We'll do example 4, and then we'll pause, and we'll come back to do the other ones in a little bit. Okay. Find the intervals. I lost my place. Find the intervals where h is increasing and decreasing. Okay. So step 1, I'm supposed to find the derivative of h. Oh, the derivative of h is already given to me. I don't have to find a derivative. That is awesome. Step 2, find where the derivative is equal to 0 or undefined. Find those critical points. Well, I'm going to set my derivative, set it equal to 0. By the way, this is not undefined. So the only way to find critical points is if there are x values that make that whole thing equal to 0. However, they did me a solid here. They factored it out. So I know either this thing equals 0 or I know this thing equals 0. So there's going to be 2 critical points. One of them is going to be if x equals positive 2, because 2 minus 2 would equal 0. And the other one's going to be x equals negative 1, because negative 1 plus 1 is 0 squared, that's 0. Those 2 x values are the only x values that would make this derivative equal to 0. So now when I go to step 3 and I build my sign chart, this time, and maybe I should make it a little bit lower, this time I have 2 x values. One x value is at negative 1, and one x value is at 2. And then I usually ask students, why are these x values special? Oh, because they make the derivative, let me use a different color here, they make the derivative equal to 0. So add x equals negative 1, my derivative is 0. Add x equals 2, my derivative is 0. But now we're going to test values around those critical points. So let's choose a number on the right side of 2, bigger than 2, like 3. And we want to know if my derivative is positive or negative. So I'm going to take that 3 and I'm going to substitute it into the derivative. Since it's already factored, I'm just going to substitute that 3 in here. 3 minus 2 is 1. 3 plus 1 is 4 squared, that's 16. And when you multiply, that's a positive. Or a positive times a positive is a positive. You could have picked any number over here, so all of these will produce a positive derivative. Cool. Let's keep checking. Pick a number between negative 1 and 2. How about 0? If I substitute 0, 0 minus 2 is a negative 2. 0 plus 1 is 1. Squared is 1. That's going to give me a negative. Cool. Keep going. Pick one more on this side. How about negative 2? Negative 2 minus 2 will give me negative 4 times negative 2 plus 1 will give me negative 1. But when I square it, it becomes positive 1. Oh, I have negatives. So what does this tell me about h? It tells me that the original function h, let me use a different color. The original function h is decreasing. Oh, still decreasing, but then increasing. How can that be? How can it be decreasing and then the derivative is 0 and then still decreasing? Oh, something like this, right? The graph is going down, it levels off for one instant, and then it continues to go down. But in all of this interval window, it is decreasing before it makes a turn and comes back up. So therefore, I can say with confidence that this is step number 4. H is increasing on the interval for x's that are greater than or equal to 2 because h prime is greater than or equal to 0. I know that that's true because my derivative is always positive or equal to 0. And then I can say h is decreasing on, well, really, it's decreasing here and here. Why don't I just say anything that's to the left of 2 on x's that are less than or equal to 2 because the derivative is less than or equal to 0. If I was asking you to find relative max and relative mins, this graph would have a relative max and a minimum, and I know that because it creates like a little valley right here as it changes directions from going down to going up. But that's not part of the question yet. This is example number 4. We're following the process. If you follow the process, you will never go wrong. We'll come back at example 5 and find out what happens. Actually, I think it's number 6. What happens when they give us the derivative graph of the function?